Okay. All my students, react to the message. Show your presence. Are you here? Or did you escape to the secret meeting that I had no idea about? Okay, cool. I need to go open a window, so I'll be right back. All right. Okay, everyone's here. Great. All right, I presume everyone is here. I'm guessing everyone is not here, but as a figure of speech, how did the assignments go? Because now we had a lot of time and a lot of assignments, and I'm hoping you were doing quite a few of them, and learned something along the way. Bad. Oh no, that's not good. Okay. Mesh stuff is hard. It is pretty hard. The tricky thing about meshes is you have to like juggle indices quite a lot, and it gets kind of abstract, and that's a little bit complicated. Didn't manage to do many of them. I got so confused when I had to convert the math to code. Gotcha. What? Salad. Hey, what's up? What? Salad is yelling. Hey! That was a weird yell. Are you okay? Are you okay? Really? What does that mean? I'm still counting this as a win. Beautiful. Looks great. Okay, all right. Then we should go through quite a few of the assignments, I think. I'm not sure if we have time to go through all of them, but I think it's good to cover some of them because knowing how to do these things is super, super useful. And so I think that's the plan. We'll go through the assignments before lunch, and then after lunch, we're going to jump into the new topics. How does that sound? I think that's the route we should go. Goodness. Actually, I did math 2 last year, but of all things, trigonometry was the one thing we didn't go through. Oh god. Why would you not go through trigonometry? Okay. Excuse me. As usual, my throat is dead. I'm just not built to talk this much. All right. I guess we can just do them one by one, like go through the assignments. Oh, I need to open my notes. Where are my assignments? Here they are. Okay. Okay. So, should we start from the top, or is there any specific ones you would really like me to cover? Because I'm not sure if we have time to do all of them, but I think we should at least do the spring, because I know some of you struggle with that one. And probably the convex polygon triangulation, at the very least. donut spring. Okay. Vote on spring and mesh surface area. Right. Sounds good. We can do this. All right. Should we start with the spring then? Or what do you think? I'm not sure how it went with the health bar. I hope most of you managed to do that one. Bézier mesh. Okay, that one might take a little bit longer. So we'll see how much time we have, but we can do that. All right. Okay, let's do the spring. So the assignment for the spring was to draw, well, a spring where you specify the height of the spring, the radius, and the number of turns it should coil around the center, right? That is, yeah, so that's the full assignment. And there are, of course, as usual, there are many different ways of solving this. There's no one right answer. But one thing that I would recommend when it comes to drawing your own shapes like this, like there's no unity function for drawing a like spring or the spiral like this, right? And so one of the things you have to do in order to do this one is a function that can draw any function. Kind of similar to what we did with the Bézier curve. Cats have zoomies in the background. So, Jesus Christ. So what we did with the Bézier curve was that the drawing function itself is entirely separate from the function for the Bézier curve. And so the function, this is just a mathematical function. Given some input parameters, we output a point. And then, boys, don't unplug the computer. They've done that before. So the function is entirely separate, and this makes it really, really useful because one thing you might run into if you start writing your math function in here is that you might start coupling the detail level and the point drawing with trying to figure out, okay, if we're on point number 6, what point should we get from the Bézier curve? And that can get really confusing. And you tend to like mix up all of your indices and offsets and all of that stuff. And so usually it's much more straightforward to separate that out entirely and just make the math function in isolation. And then you just call it when drawing your thing. So I would recommend doing this as the first step of like having your drawing entirely separate from the math function that defines the shape that you want to draw. So that's kind of the first step. So let's make a script. Spring. The math we need to use is Hooke's law? No. I'm pretty sure Hooke's law is for oscillating motion, right? But in this case, it's just the drawing of a spring, right? All right. So no functionalities needed for this one? Nope, it is just to draw the gizmo itself. So no dynamics or anything like that. No physics. All right, so first we need our drawing function. And so we're gonna make it similar to the Bézier curve, where we have a for loop. In this for loop, we iterate for some number, because we have to specify the density of at which we want to sample the math function. And so I think this kind of just depends on how detailed you want it to be. If you draw only like 10 points, then it's going to look very coarse and not very good. If you have 100 points, it's going to look pretty okay. So usually we want to be able to specify the detail level of drawing this curve, because we're approximating drawing a curve using just small line segments. Let's make it detailed. Okay. And we're going to have our function return a point. And so now we also need to decide for this math function, what should the input parameter be? And this is actually a choice we can make. It could be almost anything. So if we go back, I don't know, Photoshop open. Let's open Photoshop. You know, I updated Photoshop in hopes of them having fixed the bug where when I zoom, it flickers. They have not fixed that. So we still have the flickering. And I've had this issue for 3 years. Thanks, Adobe. Can you tell this bug? It's really annoying. You know, we are running out of space here. I think we have some room to squeeze some stuff in. What is up with my brush? Okay, cool. So for our assignment, we have a number of turns in our coil, right? Apologies for not being able to draw a coil very accurately. Great. This is our spring. We did it. So our spring has a few parameters, right? We have the height. Should make sure to use the same colors as the assignment. So the height is how tall it should be. So we got the height. And then we also have the radius. And so the radius is, as always, the distance from the center out to the edge. That's going to be the radius. And then we have the number of turns. And so this number is something you should be able to tweak. So you should be able to tweak all of these. Jesus Christ, they're just flying around. Keats. Hey. Hey. Goober. Goober scooter. You're too fast. Okay. Okay. I'm just waiting for something to shatter. And so we need a number to specify how many turns this should have. So in this case, I don't even know, 3. This is like 3.5. So maybe call it n. I don't know what to call it. So this is the number of turns. Okay. And so now that we need to create this math function, we need to decide what should the input parameter be. Like the number of rings it creates? Yes, the number of times it should make a full turn. So it's doing that here, 1, 2, and a little bit more than 3. So this is like 3.5. And so when we make this math function, we need to decide what should the input parameter be, because that could actually be many different things. we could make it based on the height. So that we give it a height. So maybe we sample, we want the height at a given value, and then we return the point at that height. And then when we want to get the next point, we move the height further up, and we get the next point, and so forth, right? This is one way of doing it. Another way of doing it is that you can specify this based on angle. Because if you consider, if you look at this from top down, then you could actually traverse this based on an angle. So if this is top down, and you give it some angle, and then we want the point that angle should return, and that would give us this point right here. So we could do that as well. So if the input allows angles that are greater than a full turn, then we could actually know the height given the angle as well. So assuming we pass in an angle that goes beyond 360 degrees. That's one way of doing it. So then we're parameterizing this by angle. Or like I said before, we could parameterize it by height. Or the one that is likely the easiest for this assignment is to parameterize it from 0 to 1. In other words, the input value of 0 should be the start of the spring, and the input value of 1 should be the end of the spring. So this is more akin to what we had in the Bézier curve. We pass in something called a t-value, and t is in the range of 0 to 1, right? I guess you would specify that like this if you like math. So a t-value is probably easiest in this case. And this choice of how to parameterize functions can sometimes be a little tricky, but usually a good fallback is to use the this formulation where you just pass in a t-value, you have a range from 0 to 1, 0 is the start, 1 is the end, and then you work from there, right? Okay. So, that's going to be our input parameter. We're just going to call that t, and that's it. Speaking of, I need to have some tea. I made some tea, and I need to drink tea. Okay, any questions so far? Hey, boys. Hey. Hey. Here's a cat update. Nice paw toast. So are we using angles to determine height or another sort of value right now? So we could use angle, but in this case, we're going to use a percentage, a t-value from 0 to 1 that represents the percentage from start to end, basically. We could parameterize it by angle, or we could parameterize it by a height value, but we're choosing to parameterize it from 0 to 1, and that's going to represent the start and the end, or the range of the full spring. So something like that. So you wouldn't have to, or I guess it depends on what your input value is there. If your input value is from 0 to 1, I think I would have to see the rest of your code to tell, because generally you would use lerp for that, or just multiply height by value. It might be equivalent to a lerp in that case, just because you have 0 at the start, but I could be wrong. I'm not sure what that function is used for. If your value is a y-coordinate, then that would give you the 0 to 1 range, if that's what the input is to that function. Thor is yelling too. Oh no. Okay. So let's implement this. Or actually, I guess we first need to think about what we actually want to do. So from 0 to 1, that's our input value. So what we then need to figure out is where is this point as we increase this value from 0 to 1, right? We need to figure out this location that's here. And there are a few observations we can make that are really, really useful. And so first off, one of them is that the three main axes are actually treated very differently. So if you consider the axes here, where we have, I guess, so if you consider the axes we have the x-axis, and we have the y-axis. I'm drawing it a little bit rotated now. And then we have the z-axis. If we think about what happens to these three coordinates as we increase t from 0 to 1, in other words, as we traverse this coil all the way up. And you can see that if we only focus on the x and y coordinates, then it kind of looks like this, right? We just have a circle. We have our x-axis and we have our y-axis. And as we increase t, we should just get the vector pointing in a specific direction. So we want to convert from our t value to an angle, and then we get our point out of that. So that's what it looks like when we look top down, right? So if we look at this from above, all we see is a point that is rotating in a circle, right? And so what you're seeing here is usually what's called a projection, similar to what we've done with the dot product, project something onto another thing. So this is the orthographic projection, the top-down view of our spring. And so in order to calculate what angle this should be, this is purely based on the t value and the number of turns across the whole thing. So if we just do it based on the t value, in other words, the let's call this angle alpha. So if we base our angle off of, if we say that our angle should be our t value, the input t value to this function, multiplied by tau. Then we have an angle in radians. And what this is going to do is that it's going to traverse one turn around the whole circle. One turn around the whole circle across 0 to 1. So this would just be one turn. So this would not actually do the number of turns that we want it to do, right? Should probably give this a different color because we used green for the angle now. Why is not y pointing up? Because I decided to orient this. Spring along the z-axis, specifically because the xy plane has kind of a special behavior compared to the z-axis in this case. You could orient whatever way you want, because again, you can rotate objects. And it all depends on how you want to orient your spring, right? If you wanted to point forwards, then you would orient it like this, because in Unity, Z is forward. In other words, the blue one is forward. But how we draw this one is kind of up to us, right? And then if we rotate the coil, then obviously it's going to change orientation, right? So it's just an arbitrary choice. Okay. So we now have a way to get an angle from our t value. So again, t is from 0 to 1, and then tau is a full turn in radians. And so as we increase t, the angle is going to increase all the way around to a full turn. But that's just one turn. We want it to turn n number of turns, right? And so all we have to do is to multiply this by n. So if n has a value of 2, then it's going to turn twice as far, right? If n has a value of 3, it's going to turn 3 times as far. And since angles repeat, it's going to repeat n number of times. And so if we just look top down on our circle, or on our spring, this is effectively the solution for that. But of course, that's just half of the solution. We also need to deal with the vertical aspect of this. But if we think about the coordinate of the point here, it is actually moving upwards at a linear rate. And so if we ignore the x and y axis, or x and z axis, I meant x and y, sorry. So if we just consider the vertical component here, or the lengthwise component, then all that's going to do is that as we increase it, it's going to just move upwards, just linearly based on the t value. And so the z coordinate in this case is just the t value times height. And so now we have all three components. We have x and y from our angle to vector formulation. And then we have the y coordinate simply from t times height. And so our final function, so this is a function of t, right? So this is going to be a vector. And so the x coordinate is going to be the cosine of alpha. And the y coordinate, sorry, and then we need to multiply by the radius. I kind of forgot about the radius. So let's just slap that in. Because cosine of alpha and then sine of alpha, this is what we use to convert from an angle to a direction, right? So sine of alpha times the radius. That's the x and y coordinates. And then for the z coordinate, which is the lengthwise coordinate, then we just take our height and multiply by t. So height multiplied by t. And so this is our final function. There we go. And of course we need to include this because this is also part of that equation. Okay. All right, did that make sense, the process of getting here? Are there any questions? We're also going to implement this in code. Okay, no questions so far. All right. If some of these things seem kind of arbitrary, it's because like sometimes you, it's mostly about like getting used to sort of a problem-solving mindset, because quite often the solution, when you look at it, looks pretty simple and obvious once you see it, right? But getting there is the hard part. And that kind of goes for all of the assignments we've done, for the most part. And so usually it's something you kind of have to practice and learn. It's kind of hard to come up with general like ideas for how to solve any math problem. But yeah, it's something you usually get used to after a while. All right, so let's implement this. Let's see if this works. We didn't quite finish our drawing function, so we should do that first. So let's see. We want to first get the starting point of this, because if we want it to be a little bit more optimized, we probably need the previous points. So get spring point at t equals 0. And then we start the for loop at 1 because we're skipping the first one because we just did that one, right? And then we want our new point, or actually we need the t value first. So this is going to be a percentage. It's going to go from 0 to 1 all the way from the start of the spring, where it's 0, and then all the way up to 1 at the end of the spring. So we want a value from 0 to 1 as we traverse this for loop. So we need to specify that here. And that's going to be I divided by detail minus 1. The minus 1 is to make sure that it ends at exactly 1. All right, and then we get our new point. So this is the point we sample in the spring. So get spring point at t. And then we want to draw that line. So we draw a line from the previous point to the point we just sampled. And then we assign the current point to the previous point. So we have that next time around. You could do it this way, or you could have a list where you store every point first and then you draw between every point. There are many different ways of doing this. In this case, I'm just calculating the next point, drawing a line, calculating the next point, drawing a line, and so forth. Okay, so this method right here, the code that we've written here, can be used for any math function. We can replace get spring point with basically whatever we want, and it's gonna draw this function. So what this does, it's basically drawing a math function from 0 to 1. That's what this whole thing is doing. And so this again could be anything. So now we're kind of ready to just shove in our math here. Okay. So first I might want this to draw in local space just so we can move this around. So I'm gonna set the gizmo matrix to transform.local to world. And then we need the parameters. We need the height of the spring. So height. I don't know what to set that to. Let's give it a range from 0 to 4. And then we need the radius, and it's going to be a range of 0 to 2. And then we need the number of turns. All right. Or maybe a turn count. This could be an integer or a float. Up to you. The math will work either way. But we might just keep it afloat to make it smooth. Okay. So now I believe we are ready to do our spring function. And we basically have 2 steps. One is to get this angle right here. So let's first calculate that. And so that is going to be t times tau times the number of turns. So t is our input value times tau, which we have somewhere else. Where do we put that? It's in the clock. You know what? We're going to take our math utilities and we're going to move them into new script because that's what you usually do. All right. We got our FutureGames math script. Here we go. Boop. All right, now we have tau. We can access from other places. Isn't that neat? So now we do mathfg.tau, mathfg.angle to direction. Okay, so we do t times tau times the number of turns. Thor? Yeah, you have water. Yeah. Okay, so So math fg dot tau multiplied by the number of turns. So turns or turn count. Okay. We got the angle, and this is the angle in radians. Thing to keep in mind. All right. Then we need the xy direction, and we could actually make use of our function that we wrote before, the angle to direction function, and because that's effectively what we need here, right? We have an angle, and then we need a direction. This is only a vector 2 because if we just look at the top-down projection, we just have an angle and a 2D direction, right? If we ignore height. So we can call this what do we call this? This is the xz vector. So we can use our mathfg, angle to direction, pass in the angle, and then we multiply that by the radius. And then finally, we can return our new vector 3. We do xz vector dot x. This would be slightly shorter if you wrote this in a shader, but unfortunately we're not in a shader right now. So we get the x and y components from the xz vector. And then for the z component, that's our height. And the height is simply height times the t-value, or total height times the t-value, right? So t times height. This should be it. I don't think there's anything more to this. Unless I missed something, and then we have a fun bug to work on. All right, let's see if it actually works. Turn on some grid, and let's snap it, and recompile. This looks like some sort of spring. The radius is very large, so let's make that smaller. Let's rotate it as well. All right, let's increase the turn count. We got more turns, and we can change the height, and then it's going to compress and stretch. And there we go. That's our spring. We did it. Just becomes a line at 0. All right. That's it. Any questions about that? That looks so satisfying. It does, doesn't it? Especially changing the turn count. This looks really nice. What's this useful for? The spring itself is pretty much useless, but knowing how to use sine and cosine this way is really useful. So sine and cosine, you use that anytime you need to go from like an angle to a direction. Like maybe you have a bullet spread and you need to specify like angular offsets like on 2 axes. And then all of a sudden you need trigonometry to do that. Or anytime you need to like place something in an arc, kind of like the budget cuts assignments where you have to make the inventory like thing, right? Or if you actually want to animate something in this fashion, then you could also make use of this. So yeah. I guess curved arcs. You could also use it for curved arcs, yeah. Like you might be making a, like, I don't know, a game with like railroads or roads that have like very clean 90-degree turns. You could use trigonometry to get a position along that turn as well. So you can use that for that. And so there are many use cases for sine and cosine like that. Anytime something circular is involved or something something involving angles, then you're going to make use of this. All right. I hope that made sense. I hope it sort of makes sense at least. All right. Should we move on to the next, or? I'm guessing we should move on. I'm interpreting the silence as I'm not sure. I think everything is fine. All right. So the next one is to create a. Oh wait, we had the color blending as well. Yeah, let's do the color blending. Why not? That's a suspicious sound from the bedroom. Okay, I just need to make sure the kittens are not chewing on cables or something. Can we make it a gradient color? Yeah, we can do both. Let's start with the easy one, and then we can do the actually also kind of easy one. So when you want to blend between two different things, either you want to blend from a position to another position, then the most simple blending function is called lerp. So this is the one we talked about earlier, where you can use this function to blend from one state to another based on a percentage. So in this case, it would be from 0 to 1, not 100. So it's kind of like a fraction. So 0.75 would be 75% of the way from A to B. And that's a lerp, or linear interpolation. Linear meaning that we draw a straight line from the first data point to the second data point. And so that's what we need to do. We need to do this with colors. So we want to have one color at the start and one color at the end. And fortunately, we kind of parameterize this already with a t-value. So we can use that directly in our blending function. So if we start with a lerp, then we need two colors. So start color, or color start, and then color end. And then let's just give them some nice colors, and make sure to set the alpha channel. If the alpha channel is not set, it defaults to 0, so it's usually invisible. And so you want to set this to some reasonable value, and then the end to some other reasonable value. Okay. And so we have our t-value here, right? And so all we need to do is to get a color given our t-value. So color c equals, or just color, actually we can just do gizmos.color equals color.lerp. And we could also, in this case, we could use lerp unclamped. Clamped just means that if your t-value is outside of 0 to 1, it clamps it to 0 to 1. It confines it to that range. Unclamped means that if you have a t-value that's outside of 0 to 1, it's going to extrapolate, as in it's going to go further than the line itself. And so this is a really important thing to keep in mind, because quite often which one you use matters. And so if you consider a lerp between, if you consider a lerp between 2 points, you have a point here and a point here, then 0 to 1 would be the range here, right? But if you allow for extrapolated values or unclamped lerps, if you pass in the t value of like 1.5, then that's actually going to extrapolate all the way out here. Because this is the range of 1, and then this 0.5 is halfway along this line. And so it kind of just multiplies the vector from A to B by 1.5. And that's the final point you're getting. And so you can extrapolate using unclamped lerps. And the same thing goes for if you have t equals negative 0.5, then you would end up over here. And so you can use lerp to extrapolate as well. Unity's lerps are generally clamped by default unless you use the unclamped variants. When you're coding in shaders, however, shaders are unclamped by default. There's a bit of a difference there that you might need to keep in mind. Anyway, the unclamped lerp is also a little bit cheaper. So if you know that your values are going to be between 0 to 1, unclamped is going to be more performant, in case you're writing performance-sensitive code. Long story short, we want to interpolate between color start and color end based on t. And there we go. All right, so recompile. And there we go. Now our spring has a nice little color gradient to it. Isn't that cute? Yeah, we did it. Might want to increase turn count. And then you also asked about how to do it with a gradient, so we can do that as well. So Unity has a type called a gradient that you can use. So we can just do color gradient. And this actually has an inspector thingy where we can actually define a color gradient. So if we recompile, and then we have a color gradient here. So if you click this, you get the gradient editor in Unity. So here you can kind of define your own color stops and specific color functions and whatnot. And then instead of doing color.lerp unclamped, we can simply do color gradient.evaluate. And then this one has an input value from 0 to 1. And so that's just our t value. So we can recompile, and there we go. So now it's actually using the gradient we have here. So we can swap out the gradient, and we get a different vibe. Yeah. So there we go. Can make this lerp color work with the handles.draw a polyline. Yeah, that one, it's kind of annoying that they don't expose colors. What happens if you tie the color to delta time? Will it flash or will it flow along the lines? Remember that delta time is just a number that represents the time since last frame. So it kind of depends on what you want to do with it. Like, what do you want to animate? You could animate the t value for the color. Sure, you could do that. You could animate an angular offset for the spring point. So it all kind of depends on like what you want to do with time. But yes, you can animate whatever you want, basically. Like it acts like a pendulum back and forth on the color chart. You could do that as well. Where you think of like the entire thing should change color. So just as one color, and then that one color sampled back and forth across the gradient, or oh, salad. Hey, come on up then. Yeah, red at the bottom, then it becomes red at the top as it flows. Yeah, I mean, you can do that. So this, again, kind of depends on how you would want to define this. But sure, we could do something like... so then we have a separate t value for the color. So here, we could do something like t plus time dot time, and then we want to repeat this within an interval, right? Because we want to keep this between 0 to 1. So then we can call math.repeat, and so now we can pass this value into our gradient, and then if we go back, recompile, turn on always refresh, we now have whatever this is. Why is this not updating real time? Am I getting the same bug as that other person got? I think I might. Or am I misinterpreting the... I might have to use... this one? That's weird that it's not continuous. Okay, there we go. That works. Okay, so it's just that time.time doesn't work well in edit mode. I think that's it. So then we should probably make a gradient that like repeats. So then we might want something like something like this. So now it smoothly repeats. This might be a stupid question, but why is green used in RGB instead of yellow? So, ooh, this I don't know how much in depth you want me to go on this, but here's a the short version of it is that our eyes can actually be subdivided into sensitivity for those three primary colors when it comes to additive blending. We're going to talk about this when we talk about shaders, but there's a concept in when dealing with colors where I actually don't have the primary colors on my thing. But so when you have a color red, for instance, and then you have the color green, then if we add these together, like as if they're light sources, so if you're shining a light that has a pure red wavelength and a light that has a green wavelength, the sum of those two will actually become yellow. And so this type of blending is called additive blending. So it's as if you're shining light onto something. So you can see that the color in the middle is yellow. And then if we also add blue, then you can see that I need a new layer. So if we also add blue, you can see that we now get more colors than that. We now have magenta, which is the additive color between blue and red. And then we have cyan, which is the additive color between green and blue. And then white is adding all three together. And so this is a very natural way of splitting up the primary colors for the way that our eyes work. And so this is called additive blending. The other option is called subtractive blending. And that is used when you're doing print. So that's when you have CMYK instead of RGB. And that is the, guess we can use multiply in this case, same thing. And so that has a similar thing, but in this case, you have 4 primary colors, where you have yellow, and then you have magenta. And you can see that when you multiply these together, or when you do subtractive blending, you actually get red when you blend these colors this way. And you can get colors in between as well. Like this is something you can smoothly blend between. And then finally, we need cyan. And so if we do that, then you can see that we now have all of our primary colors, basically. So when you are rendering things in games, or when you're using light sources, and your monitor is a light source, so pixels are divided up into red, green, and blue, and then if you increase the brightness or decrease the brightness of each of those LED lights, you can combine any color within the range that those LED lights support, basically. And then when you're printing something on paper is white usually, and so when you're blotting ink to it, you actually only need these 3 primary colors in order to blend, in order to create any color on paper within the range of these primary colors. So that's how printing works. Usually they also have black separately because it's a very common color and you don't always want to mix all 3 every time you want to draw black. So usually you also have black on top of those 3 primary colors. Anyway, so that's color mixing. Also, we should go on our first break because we haven't had a break. So maybe that's where we should do it. So let's do a break until 10:15. Okay. All right. How's YouTube chat doing? I don't know of any books for math. I'm sorry. I did not really learn from books, and so I don't have any book recommendations. So I just don't know. I'm sorry. I'm sure there are great books out there. It's just not something I'm aware of. Black is not a color. You know? How deep is your love, Freya? I don't know what that means. That's a very confusing question. It's very broad and ambiguous. Do I make more tea? I think I might have to make more tea. It's a song. Okay. Okay. Why did you post so many names of songs in chat before we started? I'm really confused. So when they told us in elementary school that red, blue, and yellow are the three basis colors, they kind of lied. Yeah, so when you're in like school painting for the basis colors, then these are kind of your primary colors. Because then if you're painting on white paper, this is similar to how colors blend when you're doing pigment mixing. Because if you have pigments in your paint, the pigments combine more similarly to this than they do like this. Yeah, and so that's why when you when you mix blue and yellow, you get green. And that's exactly what you see here, right? You have yellow and then technically cyan, you get green. Aren't those colors negative? Yes, they are the inverse of the additive one. Yeah. Okay. But yeah, color blending is a whole topic. So this is usually called additive blending, and this is usually called subtractive blending or multiplicative blending. Yeah, and it's kind of interesting that most painting apps actually have incorrect blending, which is kind of frustrating. Like if you're a traditional painter, there are very, very, very few like painting apps that actually do correct pigment mixing. There's been a few models recently that some people have developed that can actually mix colors in a very performant manner in a way that is similar to how paint blends. Shit, I forgot what the name of the app was. Oh, here it is. Okay, this is super neat. So there's been developments in this very recently with color mixing and how to like convert the more traditional types of mixing that you have in the real world in a painting app. And this is actually surprisingly complicated to do. It's not just about setting things to like additive or subtractive or whatever. And they actually worked out a really efficient algorithm for doing this, which is really cool. And it's kind of a shame that most painting apps don't do this and they don't support this, which kind of sucks. But I'm hoping it's gonna get a wider adoption soon. But I think it's a really cool technology. Yeah, there is an app. I think the technology is called Mixbox, but there was an app that implemented this. Where is it? Yes, that's the one. Rebel. Thank you. This, I think, was one of the first painting apps that implemented this. Might even still be one of the few that has it in general. But yeah, this one. This one has proper color blending. It's pretty cool stuff. Okay. I haven't used it yet. I'm still stuck using Procreate and Photoshop. Okay, if I need to make tea, I should make tea now. Otherwise, I'm gonna run overtime again. I'm so bad at keeping time. Where's my cursor? Some voice happening. I think that might be in the bathroom.
Kids.
Okay, hopefully you're gonna get some flying cats. Oh, hey.
Hey. Boys. Hey.
What? Toast. Hey. Hello. No, wait. Hey, that's my gizmo. No. No. You stole my gizmo. No.
Illegal. Yeah, that's illegal. No. No steal.
Okay. I'm just gonna get my tea. Okay. All right. Let's resume. Just to make sure Thor has water. Okay, he was actually almost out of water. Look at this boy. Whoa. Kids. All right. get into color? I forget. We were doing gradients. And then we got into color mixing. Oh yeah, someone asked, why is it RGB? Specifically. Right, okay. That's how we got into this. All right, let's continue. Or do you want the cat camera? Let's do toast. All right, let us resume. React, show your presence. GameCube? Why a GameCube, of all things? All right. Okay. Looks like we have people are somewhat here. Okay. GameCube uses a gradient color on its menu. Is that why? All right. Where were we? Right, we were doing the spring. And we got a little bit sidetracked because we were doing doing some color gradient stuff. Yes, okay. We can do more of stuff like this depending on how much we want to get into procedural animation after the break. So we can continue doing similar things like this if you want. But we should move on to the donut spring. So I'm gonna turn off our flashy gradient thing. And we're just gonna go back to the static gradients to make it a little bit less distracting. Okay. Let's bring it back to just white for now to make it a little bit more readable. Okay, so we now have a challenge. We're gonna make a donut-shaped spring. And so when you want the shape of a torus, the torus has 2 radii. So it has a major radius and a minor radius. And so we need to be able to specify both of these, and then all of this should adapt, right? So let's start by setting up those parameters. So I guess the radius we have right now would be equivalent to our minor radius, right? And so I'm just going to rename that. So that's going to be a radius minor. And then we have radius major. Then maybe we want to be able to toggle between these 2 modes. Torus mode. So we can toggle torus on and off. Okay. So got our radius minor set up, and we have our height, turn count. Okay, everything's working. So now we want to be able to enable a torus mode where we can then set a major radius, and then we want this to coil around a circle effectively. And that kind of creates the shape of a torus. All right, how do we approach something like this? So this is actually not that different from what we had before. Let's just merge some layers because I don't need those. All right, so I think the first thing we need to kind of realize is that the only difference is really how we handle height and what coordinate the center of the coiling should be at. So for this height, the center of rotation, kind of the axis, is just a straight line. But if we make a torus, it's going to be a circle, right? And then the torus will coil around kind of like this, right? And so the first thing we need to do is figure out, okay, what is the center point of our, what is the center point of this coiling based on our t value, right? Because we have a t value for going from the start to finish. And in this case, the start to finish is around this circle, effectively. And so from t equals 0 over here, so 0, and then 0.25, 0.5, and then 0.75, and then back to 1 at the start. And so the first thing we need is that center point. And we've kind of already done this, right? It's a very similar situation as this, except this time we don't factor in the number of turns. Because now we want one turn around this like donut center for across the range of 0 to 1 for t. So that's kind of the first step. But then we also need to do the coiling itself. So previously we could kind of just hand wave the way that we do this. We're like, okay, we have our coiling, and we wanted to coil, we wanted to rotate and set values for specifically the y-axis and the x-axis. But this time, we can't use the local space y and the local space x anymore, because now we basically want those direction to depend on where we are on this donut, right? So effectively what we need to do is that for a given point in our donut, we need to be able to get an x-axis and a y-axis, because now this depends on where we are on the donut itself. And so we could also define a z-axis that's tangent to the center donut. And then this will basically define the new coordinate space that we need to coil around. So if you sort of imagine the circle that this forms along the local y and x coordinates, then in this space, we can then get our point based on the same type of coiling that we did before. But the crucial thing is that this coordinate system changes depending on where we are in the curve. Like this, right? So it's kind of like rotating and moving around the donut. And so we need to figure those out. And we can notice a few things. So first off, we don't really need the z-axis in this case. We just need a point on the, in this case, the x and y plane, right? Like this disk right here is what we need a point on the circle around. So the z-axis is kind of unnecessary here. The y-axis is always pointing in the same direction. That's always pointing up, right? No matter where we are, it's pointing in the same direction. So the only one we really need to figure out is the x-axis here. So given a point on this whole circle, how do we figure out the x-axis? Well, the x-axis is simply the direction from the center to that point. That is the x-axis. So we just have to take that direction and normalize it, and then we have our new axis. And then, of course, the y-axis we'll get for free because that's just always pointing in the same direction, so we can just hard code that. And then there we go. So that gives us the kind of the local coordinate system of the point along the donut itself. And then once we have that, we can kind of apply basically the same math as we did before, where we just rotate around this local circle, and then we end up with our coil, coiling around the donut shape. Okay, that's what we need to do. So let's do this in code. Oh, the kitten's left. Okay. Oh, there's a salad behind me. Is the forward just the tangent? Yes, the forward would be tangent to this circle. All right. So let's see what actually has to change here. The angle here is going to be the coiling angle, right? Like the angle for the minor twisting. So let's call this coil angle. And this can actually stay the same. We can actually make use of this xz vector even if we're doing the donuts. So all we need to change is what we return after this. So not donut mode, torus mode. So we're not in torus mode, we just return that. Which chat should I be in right now? This chat, the one you're typing in. Okay, gonna get my tea. I think it's done.
Salad. Hey. I found a salad. Okay.
Where's my pen? There it is. All right. So now we need a few things. So first off, we need the current center of the torus given the t value. And so that's going to be the point here. This point. So what do we call this? We can't call this center because that kind of sounds like this one. I don't know of a good name. Do you know of a good name? Do we call it C? Just to make it kind of center, but not really. Let's call it C. That's our point. Let's call it P actually, because that sounds more like a point. P, there we go. We need to figure out P. What is this point given our t value? And if our coil starts, or if the donut starts over here, let's say, then figuring that one out is going to be relatively straightforward. We just do our good old angle to vector. So we get the angle here. So we do t times tau to get this angle. And then we do angle to vector, or angle to direction. Then we get a normalized vector. And then we multiply that by the major radius. And then we get that point. And this will also be useful because this is the x-axis. So this happens to be the very same axis that we're going to need for this local coordinate space. So we're going to need this. So maybe we'll call this the p direction or something. Okay. So let's do that first. So we're going to use our angle to direction, and we're going to get a 2D direction in this case. So math, what did I call it? P direction. Math FG, angle to direction. And then we pass in t times tau. We could optimize this by caching this. Jesus Christ. Okay, the kittens are doing something weird. Hold on.
Hey! What are you doing? Hey! Oh. Hey!
I don't have the FG lib you just made. I made it a few seconds ago, or a few minutes ago, on stream. It is just the same functions that we put in the, I think we put it in the clock before. I just moved these out to a separate thing so we could use the same functions elsewhere. Nerd snipe with the pigment mixing. You know? That's how it goes. Enjoy, have fun in the rabbit hole of pigment mixing. Okay. So the we have the angle to direction function now, and so this will give us the direction to the point here. So this gives us this direction, p direction. But then we need the actual point here, which is going to be the origin of the coiling that we want to do. And so this origin is, we can calculate that by doing our p direction, multiplying that by the major radius of the torus. So that gives us the center point. And then we need to define the two axes here. So this kind of depends on how we've oriented our spring and which direction we want this to be in. So this is going to be a little bit confusing because we're kind of mixing different spaces. But effectively, if our torus is oriented like this, which it is in this case, the way that I've defined it in code, then we are going to have coordinates like this. Coordinate spaces in general takes a while to get used to. You will very, very, very often run into space transformation issues, having things in the wrong space, and so forth. And it never really fully goes away. You almost always mess something up with different coordinate spaces. And so in this case, the local y-axis here is pointing in the same direction as the the torus object's z-axis, right? And so that is our up direction in the torus space. So maybe we'll just call that the local up, and that's going to be a vector 3. And so that is just going to be vector 3 dot forward because that's the z-axis. Or we can just type it explicitly, 0, 0, 1. So that's our local up. And then we have the p direction here is actually the local right axis. So we have all we need now to get this point based on our xz vector that we did before for the local direction in that space. And so all we need to do now is we do return the p plus, so p is this point right here. So p plus the xz vector's x-axis times the p direction. So that will give us we have our local direction here, and then we multiply it by these two vectors to effectively transform it from local to world, or in this case from the local circle to the torus space. And so we just multiply the components by each of these two directions. So it's going to be xzvec.y times the local up. P direction could be a vector 3 in this case. And then p should also be a vector 3. And there we go. I believe that should be it. You could also do this using matrices if you want to, but I believe it's going to be a little bit more expensive because matrices also take scale into account and whatnot, and so this is a little bit cheaper. There are a few optimizations you can do because like you aren't actually using x and y from this local up. But anyway, so this should do it, I believe. I could be wrong, but I think that's it. And there we go. Oh, we forgot the minor radius, I think. No, radius minor is here. Okay, so we do take that into account as well. And so now we have our donut. So we can change the major radius, and we can change the minor radius to make this little tiny squiggle, or we can do a very dense squiggle, and then there we go. So it's gonna be disconnected as soon as we have a turn count that's not an integer. And so for 6.5 turns, it's not going to repeat the patterns. So we have to have an integer to make sure that it's connected. But yeah, that's the tweet. We did it. All right. Any questions about this one? Seem to have done something wrong. Well, it looks beautiful. Here's the code. So one little optimization we can do here is that the local up, since we just have 1 in the z-axis and 0 on the other axes, we can basically just replace this where we put the xzvec.y in the z-axis here. And so this is going to be a little bit faster. So just a little tiny optimization there. Okay. But here's the code. So there you go. I'm gonna have some tea while you observe the code and while the kittens are trashing the bathroom.
Boys?
I don't know what's going on over here. I don't see it. I don't really see what's wrong either. That looks like it should work. Is your input t value from 0 to 1? Yeah, that looks like the same code. Works for the spring, but not the Taurus then? Well, have you set your major radius? I think your if statement is slightly cursed since else is grayed out. The reason else is grayed out is because you don't actually need an else here. You can just do return immediately because the else is kind of implicit. I think that's why else is grayed out for both of us. Otherwise, I'm not sure what's wrong. That one shouldn't matter. The order of multiplication doesn't matter in that one. Okay. I don't know why it's not working. Yeah, I'm not sure. But I should probably move on. We can look at it later if you want. Okay. Okay, I know I shouldn't be reading YouTube chat, but YouTube chat is confusing me. Nothing is allocating here. I don't know why we're talking about allocations. We have no classes here. It's all just structs. And so there's no worries about allocation. So I don't know why we're talking about allocation. Okay. Cool. Then we did the donut. What else should we do? How much time do we have left? So we have an hour and 15 minutes with a break. That would be about an hour. Let's see. What should we do next? We talked about polygon triangulation, and did someone mention surface area? I forget. Which one do you want to do? Bézier mesh or concave? Okay, which one? We need to vote. Bézier. Okay. We won't have time for both of these, so we have to pick one. The concave polygon triangulation is probably going to take a while because it involves a lot of like dealing with lists and data in ways that requires a lot of structure. Bézier mesh is kind of the same. It's also got a lot of stuff. How about inventory? I think we just have one vote on the inventory. Concave. Okay, we need to. Where did... Okay, there you go. Vote, react to that post. Just react with either an ocean or a triangular ruler. It's technically called triangulation. Okay. Goodness, boys. All right, we're doing the Bézier mesh. Mod abuse to remove votes. Oh boy. All right, let's do that. Let's move this someplace else. We're doing the Bézier mesh. I might move a little bit fast for this one because there's quite a bit of code. Okay. This one, there's a higher chance I'm going to make some mistakes because we're going to have to juggle a lot of indices now. All right, so this is our Bézier mesh. Okay. Okay. Cats are playing so violently in the bathroom right now. All right. Let's see. How do we do this? We need to have a mesh that we need to assign. So just setting that up. If mesh equals null, then we're gonna do mesh equals new mesh, and then mesh filter dot shared mesh equals mesh. All right, just to have that set up. Then we need the Bézier points. I think I'm gonna I think we're gonna use the child objects to this, so we can just create 4 child objects. We don't have an object for this one yet. All right, so we need a mesh filter and we need a mesh renderer. So we're gonna give that the default material. And then we need our Bézier mesh component. It's already assigned a mesh for us. How nice. All right, and then we need child objects on this one. So Bézier curves, at least cubic Bézier curves, have 4 points. So we're gonna make 4 of those. What is even happening with YouTube chat? I have no idea. This Kukul Rokul person is absolutely chaotic, and I'm considering banning them for filling the chat with just nonsense. Okay, all right, but I'll let YouTube do their thing. Enjoy weirdness on YouTube, I suppose. Okay. Now we need to be able to get a point in a Bézier curve based off of our child objects. So should probably give these some labels. P0, P1, P2, P3. Okay. Neat.
Hey!
I don't know why they're playing so violently these days. Okay. Alright. Now we need to get a point in a Bézier curve. So we need a vector 3, get point, or get Bézier point. And then again, we're gonna have a t value for where along the curve we want to get this point. Again, from 0 to 1, as usual. We're also gonna want to be able to, let's see, we can probably just copy our old Bézier function to save some time. There we go. Then we need some points. P0 is going to be transform.getChild0.local position. And then we'll just do that for all 4. There we go. We have our points. And then, okay. All right, we got our points. We have our get Bézier points, and now I think we're ready to start doing things. So one of the important things you have to figure out here is to we have our Bézier curve here. We have our start, we have our end, and we have some control points. There we go. So now we know how to get a point on the curve itself, right? But if we want to generate a mesh along this one, then it's going to get a little bit more complicated than that, because now we need to have a 3D shape from this. Right? And then depending on what shape we want to use, we might need these directions as well, right? And so when we sample a point, we actually also need to know what is the normal of this point. Because if we want to make this thick, in other words, at an offset like this, then we need to know what direction to offset this in, because the normal is going to be different depending on where we are. And so we need to figure out a way to calculate the normal. right? All right. And so if you have a curve and we are animating a point over time, remember our t value is sort of like a time value, or rather we can interpret it as such. And then if we then animate it over time, then what this describes is really the position over time. And then if you remember from when we were talking about derivatives, if you then get the derivative of this, we get the velocity. And the thing about the velocity is that the velocity is always going to be tangent to the curve itself. And so no matter where we sample the curve, the velocity is actually always going to be tangent. And then if we normalize the velocity, we get the tangent direction. And if we have the tangent direction, we are almost there, right? Because then we have this vector, right? This red one is now the tangent direction. And we can use that to calculate the normal direction. And because this is in 2D, we can actually take a bit of a shortcut to calculate this normal. If we were to make a 3D path where the Bézier curve itself is moved out into 3 dimensions, calculating the normal is actually very non-trivial. But if we restrict ourselves to 2D, just like Flowstorm does, the game that I showed you earlier, then calculating this normal is trivial. And then you get a consistent value. All right. Yeah, and so the first thing we need to do is how do we get the velocity or the derivative of a Bézier curve? Now, there is a way to do that, and I could walk you through all of that math, or we could take a bit of a shortcut. Because if you remember, the way the Bézier curves work is that we have this lerp function, right, where we lerp based on a t value between these points. So we have maybe 0.3 or something. And so we get these points. And so we can connect those with new lines. And then for the next layer, we get another set of lines that connect these. And then for the final point, we then get a point here. The curve that this is going to draw is something like this, right? And this red line is actually tangent to the curve. And so the way that we've calculated the position in the Bézier curve, we can actually use this method, but we get the direction from this point to this point, and then normalize it, and then we actually get the tangent direction of the Bézier curve without having to get the derivative and all of that stuff, right? Which is kind of cool. So we can just use this very same method that we used earlier, but we just kind of end it early. We don't calculate this point, and instead we calculate the direction between these two. So I'm not going to do any optimization now. I'm just kind of going to skip a lot of that. So we're going to do get Bézier tangent. And so we have our points D and E. Those are these 2 points here. So this is D and this is E. So if we want the direction from D to E, we do E minus D and then normalize that. And so return E minus D dot normalized. Could also just call these get point and get tangent, because this is in the context of the Bézier Bézier situation. Okay. Oh, you're wondering how I did the numbers thing? I just used copy and paste. So I copied these 3 numbers, and then I pasted. And so then you get the same numbers. All right. So now we know how to get the tangent, we know how to get the point, and then we also need to be able to get the normal. And here's where we can actually use a construct in Unity that's very useful. Or should we use that? Maybe we should. Or we could use a matrix. Let's use the Unity thing. Okay, so basically what we want is we want to matrix good with practice. Okay, we can do matrices. Effectively, what we're looking for is we want to define this local space for every point, right? It has an origin, it has an orientation because we have these three axes, right? And so maybe we can just make a function that returns this orientation at any given point, or this local space at any given point on the Bézier curve. So we could just make one function that does that whole thing, right? Instead of splitting it up into separate functions. That's going to make it more optimized. And so I'm just going to move the tangent in here. And so instead of posts, we can use the matrix. We can remove our getTangent function. Okay. So we have our tangent, and then we need the origin. And that's going to be this. All right. So we have the origin and the tangent, but we need the other axes as well. Trying to figure out how I want to set up the matrix. So when we set up the matrix, we can do it in various different ways. We could do either new matrix 4x4, where we specify each column individually. We could do that. We could also do matrix 4x4 dot TRS, where we give it a position, a rotation, and a scale. But I think it's better to set the columns directly this time. So the first column is going to be the x-axis, and that's the one we already have, right? That's the tangent. Although we might want to orient this differently, but that's okay. It doesn't really matter. All right, so we pass in the tangent here. Although this is going to be a vector 4 because it's a matrix 4x4, right? So this is going to be a little bit annoying if there's not a way to... do I really have to do new vector 4 for all of these? That would kind of suck. Just going to make a quick helper function to make this a little bit easier. Because otherwise the code would be really cluttered. Okay, let's just call it vec4. We're gonna be a little spicy. And we're gonna default this one to 0. Okay, so we pass in the tangent as our x-axis. And then we need the y-axis and the z-axis, and then we need the origin. And the origin we already have. So we're gonna do vector 4, the origin, and then the w component of this one has to be 1. Just because of how the matrix is set up. Here it is. So this is effectively what we're constructing right now. We're setting up these axes right here. We assign the position and we assign the x-axis. So we did that here. That's the x-axis, and we added a 0 to the end. We've assigned the position, and we've added a 1 to the end there, right? But now we need the y-axis and the z-axis. Why are we using vector 4 instead of vector 3? Because the 4x4 matrix requires 4 components here. The constructor that's just what it has. And so that's why we need the 0 at the very end, because we're supplying this whole thing as a vector. And that's why. All right. Let's just split it up, make it a little bit more readable. Okay, the z direction is is easy enough because we're doing this in 2D, so the z-axis is always pointing in the same direction. It's just always pointing away. And so in this case, it is simply new vector for 0, 0, 1, 0. Should be in the z direction here. All right. And then finally, we need the y direction. Okay, so here's where we can employ a bit of a cheap trick. That I didn't mention before. But that's very useful to know. And that is that if you have in some sense, we're trying to find this green vector, right? And if we want to find a vector that is perpendicular to both the x-axis and the z-axis, then you probably know that, well, we can just use the cross product, right? The cross product gives us a vector that is perpendicular to our two input vectors. And so we could use the cross product here. And that will work. But we could actually take a little bit of a shortcut here. Because this is in 2D, if you imagine a coordinate system, let's draw the unit circle, because why not? And we have a coordinate here. Let's say we have this point. Then we have an x offset here, right? So that's kind of the x. If you imagine this line drawing distance, this would be x. And then we have y here. So there's actually a very cheap way to rotate a vector by 90 degrees. And the way to do that is something called swizzling. So if we previously had the vector of x and y, then if we want to rotate that 90 degrees, then all we need to do is to swizzle, in other words, swap components and negate one of them. And so if we do negative y, and then we pass in x as the y component, then this will actually rotate it by 90 degrees. And so if we consider this distance right here, it will give us, this point, because now we swapped these basically. So this, so this is a very cheap way to just rotate a vector 90 degrees. And you could also rotate the other way around. In that case, you swap the components, but you negate the other one. And depending on which one you negate, it's either going to be a positive rotation or a negative rotation. And so this way, you can actually get all of the 90 degree offsets. Obviously, if you want to rotate by 180 degrees, then you just need to negate the vector in general. So then it would just be negative x and negative y. Okay. So this is plus 90 degrees, minus 90 degrees, and this is plus minus 180 degrees. Is there any big difference between positive and negative rotation? The only difference is the direction that you rotate in. So you would get different results, right? Positive rotation and negative rotation. Otherwise, there's no difference. The only difference is the direction. Okay. All right, so that's just a very cheap way to rotate these. And so you can see that in, this doesn't work for 45 degrees, does it? No, this does not work for 45 degrees. And so this is a very useful tool whenever you have to get a vector perpendicular to another one, and they just lie in the same plane. And so if they lie in the xy plane, which they do here, then you can just do one of these and you will simply get the other one that you need. Okay. So, then all we need to do is to rotate it. So let's see. We have our tangent here. Then we need our normal. And so the normal, we're going to set that to, because I don't have all of my helper functions now, so I can't do this easily. So normal dot x is now going to be, let's see, we want to do a positive rotation. So normal dot x is going to be negative tangent dot y. And then the y component of the normal is going to be positive tangent dot x. So we're swapping the components here. So this is swizzling. I guess I can, wait. What? Okay, writer is confused. That's okay. Life is confusing. Wait, now it allows me to just type it in immediately? It didn't do that before. Maybe because I didn't like fully... Okay, so this is probably just going to cast it to a vector 4 with 0 as the last component. So in this case, we can just do vector 3.forward here as well. Okay. So I believe this is all we need to do to get the coordinate space of a given point on our Bézier curve. Okay. So I believe that's all we need to do to get that point. All right. So we might want to test this now. Usually I don't trust myself, so I want to be able to test this. So I'm going to create a range from 0 to 1 for the t value, just for testing. Let's call it t test. And then what do we call this? M for the Bézier matrix? I don't know. BM, MB, Besm? I'm not sure. All right. And then we pass our t value in here. And let's see. So this is the local position, right? So we should probably work in local coordinates. Transform dot local to world matrix. What? I'm so used to using shapes. God damn it. We're gonna draw a sphere at the points. So Besm dot get position. Wait. What is? Oh, yeah, I need the radius. That's why it's sad. There we go. All right, that is a pretty big sphere. Probably want to make it a little bit smaller. All right, let's see. It's got our t-test, and it seems to be following the curve, right? That's what we want. Isn't that neat? All right, but now we also need to test the orientation. Like, did we get the direction vectors right? I'm not sure if we can do this, but let's see if we can. I think it should be possible. I forget if you need the inverse or this matrix. But I think if we just multiply by our Bézier matrix, then I think we can just draw this at 0, because I think we should have moved into the space that we just defined. Yes, that does work. Okay, that means it's easy to draw the axes as well. So we can do gizmos dot draw array to vector 3 dot right. We should set the color. Color dot red. And green and blue. Up and forward. Okay. Guess we could have used a position handle as well, but too late now. All right, we got some orientation going on here, and this seems to be correct. The red one is the tangent, the green one is the normal, and then the blue one is the well, I guess this would be the binormal in this case. And there we go. We got our orientation set up. And so now that we have this, then we can basically do something similar as we did for the torus, right? We defined this local space, and then if we want to generate points in that space, we can use that space to get that point transformed into the parent's space, right? And so that's basically what we need to do here. Yeah. Okay. Whew. The next step here is a little bit like tricky. It kind of depends on how we want to define the profile of this. Because we kind of need a shape to extrude, right? We're effectively extruding something along a Bézier curve. And so now we need to figure out, like, how do we define that data structure? I'm not sure if we should get into something very complicated or if we should just do a very simple example, because I don't think we have a whole lot of time. So I think in our case, we could maybe just generate a quad strip, just this part right here. Like this surface, and then we generate that. I think it's easier to have time for that. Okay, so let's just do that for now. All right, so we know that our matrix works. We have tried it out. It seems to work fine. So I think we can comment that out now. So I think what we really want is, or I guess we can, no, that's fine. Okay, sorry. I'm thinking in real time and talking at the same time. Okay, now we need to define all of our, all of the data that we need. So this is gonna get a little bit messy. So when we generate a mesh, we need to keep track of everything we're doing and what index every current situation has. So when we generate a mesh, we're going to have numbers attached to every vertex. We're going to have, we're going to have 0, we have 1, and then maybe 2, maybe 3, 4, depending on how we define this order, right? Right? And then we're going to have to create triangles across all of these. Okay. So how do we parameterize this in terms of detail level? Maybe we specify the number of subdivisions like this. I don't know if we should specify the number of quads or the number of lines here. I think quads is easier to wrap your head around. This being one quad, right? Yeah, let's call that sections. So this is kind of a classic error. Like, I don't know if you've seen all the memes about off by one errors, but it's very, very, very common. We often run into situations where we have something like this, right? Where we have to decide how do we parameterize this? How many is this? Is this 3 or is this 4? This is a very classic problem. This is usually called like fence post problems, where you kind of have the indices of the points go from 0 to 3, but the lines themselves go from 0 to 2. And this is a classic thing where it's very easy to mix these two up and mess up which one you're supposed to use where. So that's the fence post issue. Happens a lot. Probably going to happen now, and I'm going to mess it up at some point. But that's okay. Part of learning, isn't it? Okay, so I think what I want to define for the detail level is I want to define the number of fences, not the number of posts. So I think I want to set this number for how many of these we want. And that puts the minimum value at a nice 1 instead of 2. So we need a name for these. In our case, we can call them quads, but if we have a more complicated thing, we should call them maybe segments. So let's call them segments. Okay, so we need the number of segments. And also here's a quick Unity tool development tip. There's a function called onValidate. And onValidate is kind of used to verify the input data. It's called every time you change a variable. And so if I want segment count to never be less than 1, this is where I would ensure that happens. Yeah, so I can just do segment count equals math.max of 1 and segment count. All right. Whew, I need to drink some tea. Must have done something wrong. Can't see anything wrong with that code right off the bat. So I'm not sure what's wrong there, I'm afraid. So the error could be outside of that code. Okay. All right. So if we go to Unity, just make sure that works. Got our segment count. We can set it to 1, and we can't set it below 1. That code also looks correct. I'm not sure what's wrong. I'm afraid. And I feel like I should continue going through this so that we have time to walk it through. But I could look at it after class today. If you don't fix it until then. All right, so we have the number of segments, and then we need to do two things for our meshes, right? We need to, one, we need to define the vertices. And two, we need to define the triangles. Right? Those are 2 steps. So we can just start with doing the vertices. Let's try to make it easy. So when we iterate through this curve, we want to get the coordinate of this and this. And then we move to the next step in the curve, get the coordinate of this, and so forth. And then in the end, we should have a specific number of vertices, right? So let's see. Maybe it's good to have the store the number of vertices, the total number of vertices. And the total number of vertices is going to be segments plus 1, so that we get the last post here, times the number of vertices for your profile, which is 2 in this case, right? So it's going to be segments plus 1 times 2, I believe. So 1, 2, 2 points, number of segments, but we also need to include vertices for the last one. So we do segments plus 1 instead of segments. Okay, that's our vertex count. So let's just define that, if we can spell. That's going to be segment count plus 1 times 2. We could define a constant for the number of number of points we have per profile. If we have a more advanced profile, we would have more points than just 2. But so that's where you would insert the number of vertices in your profile. Okay. Yeah, I think we're ready to define the vertices. So let's make I'm going to ignore optimization now. So I'm just going to allocate a list. All right, yeah, vertices. And then we need to make a for loop. And let's see, how many divisions do we need now? Well, in this case, we actually need the number of posts, not the number of segments, right? I feel like there should be a better name for this, other than posts. I don't know what to call these, but in either case, we need to iterate through that. So that is going to be segment count plus 1. And then we need to get the t-value in order for us to sample our Bézier matrix, right? And so that is going to be I divided by the total number minus 1, which is going to be just segment count, right? So we need to convert that to float. And we need the minus 1 because we want this to end at a value of 1. All right, and so now we can get a point or our matrix in the Bézier curve. So that's our Bézier matrix. Let's call it MTX. And at t. And then here we need to add our 2 points. So verts dot add, and then we need to transform a point from the local space of the matrix to the world space that we're using. And so we're going to do matrix dot multiply point 3 by 4 because we don't need the last column. So 3 by 4 is going to be cheaper. It's going to ignore the projective row, which is this last row is for projective transformations, which we don't need. We don't have that. And so we can just ignore that completely. And so that's why it's called 3 by 4, because we only care about this 3 by 4 region of the matrix. And so we do multiply point 3 by 4, and then we pass in the local space points. And I guess we don't really have those local space points. We could actually make them public. So profile point A, profile point B. All right, I'm gonna default those to, what are our axes again? I guess they should be vector 2s actually. I guess they could be vector 3s. It's a little cursed, but you know what? Let's just do vector 3. So we want to place them along the z-axis in this case. So new vector 3, 0, 0, negative 1. And then positive 1. So these are just the local space coordinates of the profile that we're extruding along the Bézier curve. So these could be anything. I'm making them public so that we can change them. All right. And then we just pass them in here. So profile point A, profile point B. And now we should have gone through all of the vertices that we need. All right. And so then we need to do the triangles. We're going to make a new list here as well. And remember, triangles are indices. They refer to the index of the vertex that we want to create a triangle around. And so every triangle is 3 integers. So if we want to create a triangle between 0, 1, and 2, those are the 3 vertices we need to pass in to create this triangle. And the order here matters. It follows the left-hand rule. In other words, if you make a thumbs up with your left hand, then the face normal is going to be the direction of the thumb, and the if the order you define the vertices in follows the curl of your finger. In other words, the normal of the surface is going to follow the left-hand rule, so you want to define the vertices in this order that this arrow is pointing in. So we want to define it as 2, 0, 1. And then for this triangle here, we want to do something similar. So we're going to do 2, 1, 3. Okay. And so, here we need to kind of decide what we want to iterate over. I think in my case, I think it would be easier to iterate over every segment, right? Because every segment has 2 triangles. And so it's relatively easy to just iterate around the number of segments. So that's going to be our iterator. All right. And so now we need to figure out how do we go from the current segment to the indices that we want to define. The way that I usually do this is that because all of these things are relative, as in if we're looking at this quad right here, the indices is going to be 0 and then plus some number to access these other points, right? When we do the next quad, it's going to be 2 plus some number to access the other points. And so usually the first thing I do is to figure out what is the root of this this whole quad. And so the root in this case, we can see that it's segment count, or the current segment times 2, right? 0 times 2 is 0. 1 times 2 is 2. Yeah, and then, wait. Is that not, hold on. Yeah, 2 times 2 is 4, 3 times 2 is 6. Yes, that's correct. So the root index is always going to be the current segment times 2. So I'm just going to call that S to kind of specify that this is the segment. Sometimes I rename my iterators just for that reason. So the root index is going to be S times 2. And now it's relatively easy to get the next one. So the neighbor is going to be the root plus 1, right? So the neighbor is going to be root plus 1. And then the next point is going to be root plus 2, because it's 2 plus 2. And then the neighbor of the next point is going to be root plus 3. And so in this case, it's a relatively simple offset that we're setting up here. Okay, and then we need to define the triangles. So triangles.add. We're going to have to add 6 numbers here, right? Because it's 2 triangles. Each triangle has 3 indices. And so we just do the same thing we did here. So it's going to be root neighbor next, right? That's the first triangle. So root neighbor next. Okay, first triangle, second triangle. All right, so the second triangle, we could go from this one. So this is neighbor to next neighbor to next. I think that's correct. So neighbor to next neighbor to next. Okay. And I believe that's it for the triangles. And then we need to assign this to the mesh. So we're going to do mesh.clear just to remove any old data. And then mesh.set vertices. We're going to pass our verts in. We're going to do mesh.set triangles. We're going to pass in our triangles to the default submesh index, which is just 0. And then we also haven't calculated the normals now. So we might want to do that. We can either calculate them ourselves, or we can calculate them manually. So there's a function called recalculate normals. So this one is just going to kind of do it for you. It's going to approximate it based on the neighboring vertex structure. Or we can assign them manually. I think the best way of doing it in this case is that we can just define them manually. Because we actually have the normal data from our matrix. So then why not just add that, right? So we're gonna define our normal. And so that is gonna be the matrix dot multiply vector. And then we pass in, I guess the normal is just the column, right? So the normal is the first column. So we actually don't have to transform at all. We can just get the column directly. Wait, why is this sad? Oh, because we already have a thing called normals. Normals. There we go. Okay. All right, so we have the normal, and then we just add that to our normals array. So add normal, and add that twice because they have 2 vertices, right? And they have the same normal. Cool. And then we do mesh.set normals, pass in our normals, and I believe that's it. Another thing, if you're doing this per frame, you might also want to do mesh.markDynamic. it just optimizes it for frequent updates, as the documentation says. It's going to be a little bit slower if you don't do this. Okay, I think this is enough, unless I've forgotten something. Let's see if it explodes. Recompile. Okay, beautiful. I love this. Look at this beautiful quad. All right, let's increase the segment count, and there we go. We have now created a, well, technically a Bézier surface, right? But that's our little wavy wave. Isn't that cute? We did it. We can look at the wireframe as well. We want to see the structure that we ended up having. So if we now increase the segment count, you can see that it adds more vertices. Yeah. Okay, we actually did it. Hell yeah. All that work to draw a wavy quad. Oh no. Yeah, I mean, it is a lot of work, but Blender inside Unity. I've seriously considered writing a 3D editor in Unity, but I've never gotten to it. It's a lot of work. Pro Builder is awful. Yeah. So there are already like 3D editors in Unity, and they probably spend more time on it than I will be able to. Yes, there's a Git with all this stuff. I haven't committed this code, but I should. Okay. We never ended up using the vertex count. Usually, you use those when you use arrays instead of lists, but I guess we can do a quick optimization as well, just to make sure that this doesn't allocate just out the ass every frame. So we're just going to move these out into the outer scope, and then instead of defining new ones, we're just going to clear them. Before we generate anything. Okay. And so this is defining vertices, and this is defining triangles. Right, Gustav, if your triangles are flipped so that they're upside down, then it is probably the order that you define the triangles in have been flipped, or you flipped the vertices in the profile, or passed them in the opposite direction or whatever. Yeah, that code looks correct, so I presume you probably flipped these somewhere. Where do we use the getTangent function? I actually merged it so that the tangent is returned in the form of a matrix instead. So we're kind of doing the position and the tangent directly in the same function, because that's cheaper, and why not? Because that's kind of the thing we need anyway. Yeah. And so our getTangent function is basically this part right here, right? Okay. And I will push this code. Let me just test to make sure the profile stuff works. Yeah. This seems to work. So I think we should also be able to do stuff like, whoops. Like this. Yeah. Although now the normals are incorrect. We kind of hard-coded the normals. So if you're wondering what a mesh looks like when you have incorrect normals, this is this is what it looks like. Because now the shading is confused. But we can use it to generate this type of stuff. We would just have to adapt the normals after this. But now we basically generated a polyline, right? Generated a thick curve. Okay, should revert those changes. All right. Not sure why I'm not getting a mesh. Check for errors in the console. Make sure you have a mesh filter and a mesh renderer with the material assigned to it. Double check those. Is your number of segments set to 1 or? Because that's what would happen if it's set to 1. That is weird. I don't know why that wouldn't work. I don't think I did it right. Just seems like a wavy line to me. So your points are now in 3D. So keep in mind that we actually haven't added support for Z positions now. So the orientation is going to presume that your child objects have a Z position of 0. So make sure that your points have a Z value of 0. Otherwise, you're going to get wonky results. So if you have a weird squiggle, then it's not going to be super great. Okay. Adam, I think what it could be is that your points might be defined in the other direction. Like that might be, it might be as simple as that, right? Like maybe your first point is on the right side and the last point is on the left side. Then it would be upside down, right? Maybe? Although your mesh is not, says none there. Wait, I forget if you had an upside down mesh or like a flipped mesh or what your case was. But you have to make sure that you assign to the mesh filter if it's not rendering anything. Okay. You have that. It's possible maybe you added this code later and the mesh is no longer null. So I think you could move this outside. Just assign it every androgismus. Because it's possible the mesh is no longer null, but somehow the mesh filter never picked it up when it was created. Okay. All right. How much time do we have left? We have 7 minutes until lunch. What do we want to do for the last few minutes? Any other assignments you have questions about? We have time to talk about some of these, but we don't have time to implement them. Some of you talked about the Polygon triangulation. I think that's an interesting exercise. I think we should talk about that. Let's do that as our last thing. So, all right. Let's do Polygon triangulation. So this is kind of a fun and challenging problem. Got the mesh now, but for some reason it has shark teeth. That means your triangles are incorrect. Some order somewhere is not the way it should be. But I mean, if you want shark teeth, then that looks great. Okay, so Polygon triangulation. So this is a common problem in tech art or in like 3D modeling. You have some sort of polygon, and then you have to fill it in with a surface. And so when we talk about something like convex triangulation, if you have a shape that is fully convex, then in this case, it's a relatively straightforward process to triangulate this. Because when you have a convex shape, all you really have to do is to consider one point here. And because it's convex, you can actually just draw a line to every other point. Because there's no chance that you will like accidentally like intersect the mesh anywhere. If it was concave, like if we had a concave mesh like this, then this would actually be an invalid triangle, right? Like we don't want a triangle here. But because it's convex, every point can see every other point, right? And so when you have a convex polygon, all you have to do is iterate through the oh, the parenthesis was the issue for me. Oh, so that one is doing an integer division. Yes, you have to convert one of those to float in order for the t value to be a floating point value. Yes. Okay, anyway. So when you want to triangulate a convex shape, you just pick your point, usually the first point. So if this is 0, 1, 2, 3, and 4, then all you really have to do is to say, okay, I want to create a triangle between 0, 1, and 2. Then we've got our first triangle. And then the next triangle is 0, 2, 3. And we got our next triangle. And the last one is going to be 0, 3, 4. And so it's basically a for loop where you define the indices with a bit of an offset to generate these triangles. And so that's how you triangulate a convex shape. Now, the way more hard problem is the concave shapes. And so now, if we want to triangulate a polygon that can be concave, that means we might have a situation like this, right? Just a very, very irregular, jagged, unpredictable thing, right? So now we have a polygon that is concave. So our usual strategy of just picking a point and triangulating every other edge is obviously not going to work here. Because if we consider the first point here, we can just like, okay, if we employ the same strategy, we would create a triangle here, and then we would create an incredibly skinny triangle here, and then it would create a triangle here, and then a triangle here, and then a triangle here, from here, right? And then it would overlap here. So it would create a triangle in this entire region. And so this, the strategy we used before doesn't work anymore, because now we might actually accidentally overlap some points. And so we can try to figure out, okay, so what are some of these, what are some of the properties of these vertices? Like, what is special about the vertices in a concave polygon? And so you can actually look at the internal angles, and that can actually inform us a little bit about the geometry we're dealing with. And so if we look here at the internal angles, you can see that this one is less than 180, right? And that one is 2. But this one has more than 180 degrees, right? And then we can continue. This one is less. And then again, this one has more than 180 degrees. This one is less. This one is less. This one is more. And these types of points have a name. So not only can we call the entire polygon convex or concave, but when it comes to the points themselves, this property is called convex if the internal angle is less than 180 degrees. And it's called reflex for some reason, if the points have greater than 180 degrees on the inside. And this is actually critically important when trying to figure out how to triangulate this. Because if you look at the vertices that are convex, those are way more likely candidates for triangulation, right? Like if we look at this one, and we look at its neighbors, we can actually create a triangle safely here, right? If we look at this one and its neighbors, we can create a triangle. Look at this point and its 2 neighbors, we can create a triangle there too. And so the first step is kind of like find convex points and triangulate. Just triangulate the neighbors of the convex points. And this strategy kind of works, especially if your cat will stop eating your cables. Hey! So this is kind of the first step to doing this. But this will not always work. So this is going to work on some of them, but not in every case. And so what is the case where this strategy wouldn't work? Well, consider this shape right here. We have a vertex. We have another vertex. We have a cat. And then we have a vertex down here. And then we have a vertex here. And so now if we consider the internal angles, well, it's convex here, it's a reflex here, it's convex here, and it's convex here. And so now we might just use our algorithm of like, okay, well, this one is convex, and then we look at its neighbors and create a triangle with its neighbors. And so now we've actually created an invalid triangle. Like, this is not how we're supposed to fill this shape, right? I need to eject this boy. Jesus Christ. You're getting ejected. What? Hello. You're being a piece of shit. You're being a piece of shit. You're the cutest piece of shit. Yeah. Stop eating my cables. It's dangerous and bad. Okay? Okay. Okay. Do you think he's got it? His face. He's so full of shit. You're full of shit. Okay. Bloop. All right. So this triangle is not valid, right? And so now our strategy of just picking a convex point and creating a triangle around its neighbors no longer works. But it actually works pretty okay in most cases. But so the final thing we have to do in this strategy or this algorithm is that when we're considering a candidate for creating a triangle, so this would be considering this triangle right here, right? We have to check if it contains another point. So we have to check, does it contain another point? If it does, then don't create a triangle. That's a really, really important step to make sure that this algorithm is robust. There are a few shortcuts you can take here. When you have a triangulation like this, it's actually, there's an optimization where when you're checking if it contains a point, it's actually only possible, or rather you only have to check for reflex points. You don't have to check all of the convex points. You only have to check if it contains reflex points, which is actually kind of a nice little optimization. So we don't have to check every other point every time, right? And so if we do that strategy, then if we're considering this point, we check its triangle, it contains a reflex point, and then we discard that candidate. And then we move on to the next one. We consider this one and its two neighbors. This triangle right here is valid. This is a triangle we want to fill. And our new perimeter now is this triangle right here, just one triangle left, and then we fill that in. And so that is usually the strategy that you employ. And so if we were to do this one right here, then we would start with some point, maybe this one. We pick this triangle right here. And so that one is convex. And then we fill in a triangle. Now we have a bit of a scary situation because when you have collinear points, in other words, points that lie along the same line, the algorithm gets ambiguous and messy. So hopefully you didn't run into that, or you don't have to deal with that. We go to the next convex point. We check for containing neighbors here. It doesn't seem to contain any points, right? So we create a triangle. And remember, every time we add a triangle, the perimeter of our polygon kind of shrinks, right? Like we're dealing with a smaller and smaller polygon every time. And so you need to take that into account, that the state of whether or not a point is a reflex or convex can actually change, right? And in fact, that actually happens here. So the next triangle that we got is checking the neighbors of this one, which is now this point and this point. And so this one is still convex, but this one is actually convex now, but it wasn't before. And then we create a triangle there. No, not the cables, not the cables, not again. We've been through this, Mr. Salad. Mr. Salad, no, no cables. Okay. And so the next triangle would be created here. And so we fill that in. And now the new angle of this one is actually almost 180 degrees, but it is actually a little bit smaller. So this one is now convex, right? This one is also convex now. And so we kind of keep moving on here. So the next triangle would be a very skinny triangle here, which generally, if you want a very good triangulation algorithm, generally very thin triangles are to be avoided. GPUs don't like skinny triangles. So you generally need a better strategy than this one for like a very optimized algorithm, or one that gives you a better shape rather. Okay, and the next one, we're checking this point. And for this one actually seems like it could probably contain this point. I think it does. It's almost collinear with these 3 points, but it seems like this would be inside. So we're skipping this one. So we're not going to create a triangle around this one's neighbor because it contains this points. So we're doing this one instead. We're skipping to the next one. And this one can actually define a triangle just fine. So we fill that in. This is now convex instead of reflex, because the angle is less than 180 degrees. And we can create a triangle with that one. So that's going to be this triangle right here. And that because this is the neighbors. These are the 2 neighbors of that point. And then finally, we have this angle right here is convex, 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 and it's just 1 triangle left. And that's when we fill in the last triangle. So this is kind of the strategy that you employ to triangulate. This triangulation algorithm actually has a name, and it's called the ear clipping algorithm. So that's a very useful, relatively easy to implement way to do polygon triangulation. Some of the more like mathy stuff in this, that's less about the algorithm itself, is that when you check for whether or not a point is reflex or convex, remember that we have a situation kind of like this, right? Where you either have a convex internal angle or you have a reflex internal angle. If you want to check if this is convex or reflex, this is actually kind of just a straight up dot product, determinant, right? Or the wedge product, because we have a vector pointing in this direction, and then we have another vector pointing in this direction, and we want to know, is this vector pointing to the left or to the right of this one? And that's all we need to do, right? We don't actually need like the actual angle here. Like we don't need to know if this is 135 or whatever. All we need to know is it to the left or to the right? And so we can actually just use the wedge product. So if this is A and this is B, so all we need is the wedge product between A and B, and then we need the sign of that one. Like, is it positive or negative? So we can use this to determine if it's convex or reflex without actually calculating the angle, because we don't need the exact angle. We just need to know if it's to the left or to the right. Okay. And so this one would be either positive or negative depending on which one of these 2 states it has in relation to these vertices. The sign of this one would be different depending on the winding order. If your polygon has been defined like clockwise or counterclockwise, so that's also something you might have to take into account when you're doing this. But yeah. All right, could one solution be segmenting the shape with the convex points and then recursively divide it like that? What do you mean by segmenting the shape with the convex points? We've gone a little bit over time, but I hope that's okay. We don't have time to implement this, but I think this kind of explains the process at the very least. All right. Any questions or thoughts about this or any of the other assignments before we go for lunch? Or yeah. Any questions? Have you pushed to the Git? I can do that. The convex points and the points between them are separately triangulated. I I don't know what you mean by points between them. Like, how would you check for that, and what do you mean by that? Let's see. Okay, everything's been pushed to the repository. Okay. Yeah, I'm not sure what you mean, Judith. I think you would have to draw a diagram of the process. Okay. Any other questions? We're gonna, after lunch, we're gonna do the special bonus topics that were not planned from the beginning, which means that I might fumble and I might make a lot of mistakes and I might not be qualified to talk about the topics, but it should be nice regardless. We're gonna talk a little bit about some esoteric math. We're gonna open the quaternion box, the mystery box. We're gonna open this a little bit and just peek inside and kind of try to build a little bit of an intuition about how this mystery box works. And so we're gonna do that. We might also have time to get into a little bit of geometric algebra, which is kind of fun, or at least I think it's fun and interesting. Okay. All right. Have an implementation problem like the shape I sent this morning. I'll have to look at it more. Yes. Okay. Yeah, I can do that off stream. We don't have to do that while I'm live. Okay. I think that's it for now, right? Questions? Thoughts? Does YouTube have any questions? Yes, all of this will be on YouTube. Don't worry. The thing after lunch is also going to be on YouTube. Okay. Something like this. I divide the shape between the reflex points. Then the algorithm becomes about how do you divide between the reflex points. And that is a non-trivial thing to do. It might be trivial in this case, but in the general case, it is not trivial. And it's also difficult to detect which case you're in. Yeah. So for example, if you consider, so your idea, let me see if I just got this right. Your idea is to take all of the points that were originally reflex, and basically triangulate based off of those, which would be these 3 points, right? So yes, if you create a triangle between these reflex points, then all of the other areas that are left happen to be convex in this case. So that will work with this specific shape, but it will not work with the general shape. So if you consider, well, I guess you can just make a little shape like this. Like now, what does it even mean to make a triangle out of these? And like, how do we subdivide this and whatnot? And so if you want to look into that, that is actually a separate problem, and that is called convex decomposition. So if you wanna look into that, then this is the search term. And convex decomposition is generally, as far as I know, a harder problem than polygon triangulation. In terms of algorithmic complexity, I believe convex decomposition is just much more expensive. Whereas polygon triangulation can actually be done really quickly. We haven't actually talked about like algorithmic complexity, like the O notation, O of n squared and O of 1, this type of stuff. But there are fast ways of triangulating. There are ways that are faster than ear clipping as well, in terms of how much the algorithmic complexity grows with a number of points. But those are complicated. We have data structures and algorithms in December here. Right, cool. Okay. Then you can maybe do that. And then you're probably going to talk about it there. Starting next week, not December. Oh, okay. Doesn't the dot product give me the same result as the wedge product? No. Because the dot product does not distinguish between these two cases. The dot product returns the same result for both of these. So the dot product will be able to tell you if this is behind or in front. So that's what the dot product can distinguish. But the wedge product will distinguish if it's to the right or to the left. And so that's why we're using the wedge product and not the dot product. Okay, all right. I'm very hungry. We have to go for food. We went 20 minutes overtime. Do we go for an hour of lunch or do we shorten the lunch? Long lunch or short lunch? Or I guess it's normal lunch or short lunch. Vote with your lunch money. 1 vote for long lunch. Okay. Not doing double lunch. 50-minute lunch? That's a weird compromise. I guess it's valid. That's like lerping between the two. All right, let's do normal length lunch. Okay. All right, going for lunch break. Okay. Okay, we're zooming in an hour then. Lunch break. There we go. Before I go and turn off the stream, anyone on YouTube? Do you have any questions? Wait, double audio? Do you have double audio? Is my audio doubling up for everyone or just that one person? Audio's all right? Fine there? Audio's fine. Okay, cool. Then that problem probably has 2 tabs open or something. All right. Thank you. Thank you for joining. After lunch, we're gonna do the special topics of esoteric math. That's still interesting, but maybe a little bit less relevant for games. At least when it comes to the abstract algebra stuff. We're also going to talk a little bit about splines and procedural animation, which is much more applicable to games, at least so far. All right. Well, I will see you all after lunch. Hope you have a good lunch break. Right. Bye, everyone.